All right. Good morning or good afternoon, everyone. I'd like to get started. Can people hear me?
Yep.
Thank you. All right. Today, what I'd like to do is give you a chance to ask questions about XV6 and about the recent labs. And in order to kind of give us something to talk about, I'm going to do as much as I can of the copy on write fork lab here, just to give us sort of something to chew on. And you should feel free to ask any questions you like. You can ask about why my solution is different from your solution, or why XV6 works the way it does, or why the bugs that we encounter show up in the way they do. So just to remind you, although I'm sure this is, sure I don't need to remind you, the point of copy and write fork is to avoid copying costs for pages in a fork that are never modified. I put in a few lines of code to measure the reduction in the number of bytes that memcopy had to copy during user tests for my copy and write solution, and found that it actually reduced the amount of copying by 90%. And this is for user tests, which is kind of a weird program, but nevertheless. And I think a lot of it is reductions in the copying of the instruction pages, because the instruction pages are never modified. So there's never any point in having copies of them. And I think that's where a lot of the win was from. Copy and write fork also reduces RAM use, the sort of maximum amount of RAM you ever need to use, and it reduces the amount of time you spend in fork. And so fork returns more quickly. On the other hand, of course, the total cost may be larger, because if programs end up modifying all the copy and write pages, you end up having to do all the copies plus take all the page faults, which can be a little bit expensive. But nevertheless, people have found that in general, it's a net benefit. And as you know, the main challenges are, one challenge is how to avoid freeing memory. Now we're sharing pages among processes. We have to not deallocate them, have to not free them until the last process is finished using them. So we need more bookkeeping. And the other interesting challenge is that there's, in copy out in particular, the XV6 modifies user memory without actually going through the MMU paging hardware. And so we have to mimic page faults there. I'm going to go through the lab, starting at the beginning, the copy and write lab. Before I start, I just want to just sort of mention the strategy that I think of myself as following when I do labs. And I do a lot of labs, from one year to the next. I don't remember the details of how to do the labs. And in addition, the labs change. All right, so when I'm doing the labs, I always take small steps. I find some sort of next subset of the problem to solve, maybe 5 or 10 lines of code. I program that up and I run it and try to get it to working before I go on to the next, proceeding to the next step. And this is, as opposed to, for example, thinking through and writing a complete solution before starting to test and debug it. I always test and debug a little bit at a time. A lot of the reason for that is that even though you may have sort of thought through a lot of the things, a lot of the challenges, and a lot of the design for what you're going to have to do to solve a lab, I find at least there's often surprises. And so if I implement everything first, I may find then that I wasted a lot of time because I didn't fully understand the problem until I actually got into debugging it. And the way I choose the next step at each point is usually driven by whatever panic or crash or test failure I see next. Sort of tells me what I need to fix next. And while I'm doing this lab, I'll make a few mistakes that I actually made the last time I did the lab, so that we can have a little practice debugging together. And again, feel free to break in at any time and ask questions about anything. I'm starting here with a fresh copy of the copy and write lab source, the same as all of you did. So I'll just fire this up and run the copy and write test. And maybe I'll get lucky and all the tests will pass and I won't have to do anything. Too bad, one of the tests failed. Okay, so not too surprising. And a good step at this point is to go have a look at the tests and figure out what it's trying to do. And the sad truth is some of the tests are complicated and hard to understand and don't necessarily test anything specific. They just sort of try different things to see if something will break. But luckily with this simple test, it's pretty clear what it's doing.
Quick question.
Yeah.
Do you mean to share your screen? You cannot see anything.
Oh gosh. I'm sorry about that. Thank you for letting me know. All right, is that better?
Yes.
Good. Brilliant. All right. Okay. Well, that's bug number one. Okay, so I'll just here I am in my copy and write test. I ran copy and write test, and it fails. I look at the test, this simple test on the screen at right is what actually failed. And this test, luckily enough, it actually tells us what it's doing. It allocates what it knows to be more than half the available memory in XV6 and then forks. And so, of course, the reason this fails is that fork makes a copy. In ordinary XV6, it actually literally makes a copy. And so if we have to copy more than half of memory, there's just not enough space for that. Okay, so of course, this is what copy and write's all about. And we know that the basic game is that instead of copying the process's memory, we want to just copy its page table and not the memory. So the child just has a carbon copy of the parent's page table instead of memory, referring to all the same physical pages. The place where fork does its copying is in vm.c and uvm copy. And so we can just modify this code to, instead of allocating a page of memory here and copying onto it, we're going to eliminate those 3 lines and instead just copy page table entries. So I'm actually just going to hack this copy of map pages. Since we didn't actually allocate memory here, I'm going to get rid of this free. I'm going to fix this map pages to, instead of mapping mem at address I, I'm going to map the PA, which is the physical address we pulled out of the parent's page table. So is that clear? So this will just have the effect of mapping all of the parent's pages into the child's address space.
Isn't PA already a UN64?
Probably.
Or is it bad if you were to cast it if it's already that type?
The cast does absolutely nothing other than shut the compiler up. Since addresses are 64 bits and uint64 is 64-bit, that cast doesn't change the bits. It just makes the type checker less upset. But let's see, I actually don't know what any of these types are. Oh, one thing is we don't need this mem variable. Oh, well, okay. So you were right about PA. Gosh, I wonder if we're done now. Let's run the cow test and see what happens. Oh, we're definitely not done. Okay, so what we got here is this user trap with scos of 2. Anybody remember what scos 2 is? I'll just tell you.
It's instruction failure.
It's an illegal instruction. So why would we be getting an illegal instruction now? Is this what we expected?
Did we overwrite the portion where we have instructions?
Yeah, something is damaging the instructions of the user program. And of course, the fault, we're not surprised we get a fault here, but we were hoping for stored faults to drive the copying process and copy on write. We're not getting the store fault. Any other hypotheses for this? This is not really fair because like this is my bug, not your bug, but nevertheless.
Does it have to do with the flags?
Yes, it does. Okay, so I'll just leave that to the side. It'll actually come up again. Another question is, we're hoping for store page faults, which will drive the copying process. Why didn't we get a store page fault? All right. Why would we get a store page fault? Under what circumstances does the RISC-V generate a store page fault?
We would get it if the write flag is not set, but now we can just write to everything still normally.
Yeah, I've left the write flag set. All right, so that's bug one, which I did actually make last time I did this lab. So I've left the write flag set in the parent, and I've haven't done anything to the write flags. This flags variable here is just the way we pulled it out of the parent's page table. It's all its pages are writable, and so that means that it's going to be writable in the child too. We won't get store page faults. So I'll just be sharing a page read write, which is not what we wanted. So how am I going to turn off the? How am I going to write protect these pages? Any proposals? What should I type? How about?
You can do flags and equals the wave sign
Oh, yeah.
underscore W.
Yeah. So we need the tilde there. I call that wave sign a tilde. We need to we need to clear this bit in the flags, but we want to leave all the other flags set. Okay, so that's gonna, will this clear the flag in the parent or the child?
Child.
Just the child. So how do I clear, do I also need to clear the flag in the parent?
Yes, because like we want the child to be independent for the parent. So if we write something, we don't want like the child to also get the modification from the parent.
That's absolutely right. We need to write protect the page in the parent as well, because we don't want the child to see the parent's modifications. We're trying to mimic them having completely separate copies. So what can I do to clear the flag in the parent's page table?
You can do something like star PTE and equals not PTE, right?
Yeah, so I have the parent's page, a pointer to the parent's page table entry right here in PTE. And so I can clear the PTE flag here too. So that's pretty convenient. My belief is that's enough to make both copies of the page or both mappings of the page read only. So hopefully now we'll start getting write faults.
Is it also possible to clear the PTW bit before you say flags equals PTE flags of PTE? And that way, like the original flags is just the correct thing?
Oh, I see. I'll put it way up here.
Yeah.
Yeah, why not? I'll give that a shot. Oh, seems to work. Yeah, that makes sense. Okay, so now I get my write fault, which is what we're hoping for. And hopefully what this write fault means is that one of the other processes tried to modify the page, and the RISC-V generated a page fault from that. And we're going to want to react to that by making a copy of the page and mapping it read-write. Before we do that, just to make sure that what we're seeing, it's this F here, this scause, that is sort of making me imagine that we're seeing what we want to see, namely a store fault. Let's actually go and look and see where that happened. We know it's in process ID 3. Process ID 1 is init. Process ID 2 is the shell. And so maybe process ID 3 is going to be cow test. We can look in cow test.asm and look for 9DA and see if it makes sense as a instruction that could generate a store page fault. Boy, this doesn't look so good. I can't even remember what AUIPC does, but I don't believe it performs a store. Any guesses what's going on? It'd be nice if the page faults we were seeing actually made sense. I'll tell you, it turns out this page fault occurred in the shell after the shell forked, but before it execed cow test. And so we're really looking at a wrong ASM file. It turns out the right ASM file is the shell ASM file. So we'll look for 9DA there. Ah, yes, and in the shell, 9DA is a store instruction. And it's at the beginning of this parse command function that actually parses the cow test command that we typed and figures out what to do with it, namely call exec. And it's doing a store into the stack. It's the preamble that stores the callee saved registers. And not surprisingly, that this should be the first page fault we get because it's on the stack. The very first thing most functions do after fork returns is they modify their variables in the stack and boom. Unsurprisingly, that causes a store page fault. So any questions about why we're faulting?
I have a quick question. How did you figure out it was in the shell rather than in cow test?
Because I looked at 9DA in cow test, and that is not a store instruction. I thought, gosh, what could possibly be going on? And I looked at process ID.
3, so is PID3 the shell, or is that?
PID3 is, PID2 is the shell that printed that prompt. PID3 is the next process that's created. And so initially the shell forks to make PID3, but after the fork, it's still running the shell, right? It's a child of the shell running a copy of the shell. It's going to call exec to run cow test, but it hasn't done it yet. It hasn't been able to get that far without taking a store page fault when it writes a stack.
So can you clarify, does that mean that there's like an error with the shell related to process ID 2 because it doesn't have the proper data in order for the child to have the right data? Or is it an error with process ID 3?
It's a page fault that occurs in process ID 3.
Right, but the bug that we're seeing right here, like
there's no bug. This is, I'm implementing copy on write fork. And what we just did in vm.c was write protect every single page in the parent and the child, right? That's what this line is doing. Yeah. So the next time either the parent or the child does a store from user code, it's going to be a store into a write protected page because every page is write protected. And so it will cause a page fault.
Oh, so this is the proper page fault that we want.
This, right. And I was just, all I was doing is checking that what's going on is exactly what we think is going on, as opposed to some other bug.
Gotcha, makes sense.
Okay, all right, so we took a page fault here in this store, which is presumably the first store the shell does after the fork. Okay, so now we have to handle these, now you want to do something useful in this page faults. So where's the page fault handlers and trap.c. And user fault, I think it pretty much doesn't matter where we insert code to, I mean, there's all these different cases here that user vec, this is user vec, right? Yeah, or user trap. The user trap is dealing with, we're just going to throw in another else. We're only interested in write faults. We're happy to read these shared pages because all the data is there. It's just writes we want to catch. So now it turns out, as I'm sure you know, that we're going to need to use the code I'm about to write from 2 different places. So I'm going to just wrap it up in the code that sort of makes the copy of this page in a function I'm going to call cowFault. It needs to know the current page table, and it needs to know the virtual address that we faulted on. That's stval. Sometimes it can fail because, say, it runs out of memory. Maybe kalloc will fail. So we need to prepare for a return value, and pretty much no matter what the failure is, we're going to kill this process. All right, and if we didn't kill it, we'll have cowFault return -1 if there's a failure, return 0 if there's no failure. If there's no failure, then we're going to rely on cowFault having made this virtual address writable so that when user trap returns, the process can actually continue successfully.
Is there a reason that you put, or like, is there a reason why you put this line above the else if which dev enter line?
I don't think so. Whether it's correct depends on what deventer does. We'll just take a look. The risk is that deventer might see a device interrupt for some reason, even though we are in a page fault. So we just got to check that deventer looks at scause, and if scause is F, it's going to return 0. So we just want to make sure that if if deventer returns 0, then it's going to go on to our code. So that's fine. Okay. Okay, now we need to write. Actually, there's one thing I want to observe here, and that's that if there's a failure, we kill the process. So this is unfortunate. It would be fantastic if instead, most of the time processes allocate memory or whatever by calling system calls. The system calls can return some error value, -1 or something if there's a failure, and the process can then do something appropriate if it knows how in order to deal with that failure. Here, though, because there's no system call, there's not any obvious way to tell the process that something went wrong, which is irritating. You can imagine solutions to this. For example, in some more sophisticated operating system, we could have something like the alarm user fault handler that you implemented that we could call up into to say, look, we can't continue your process because we can't fix this page fault, but we want to tell you something went wrong. But we're not going to do that now. It's much simpler to just kill the process. Okay, so we have to implement this cowFault program. Takes a page table, the current process page table is argument, and the virtual address that the fault occurred on. Okay, so the first question we always have to worry about when dealing with virtual addresses that the user program produced, like this one, is what if it's a completely crazy address, like way up above the top of the process, or what if it's an address like in the trap frame or in the trampoline page or in the page, the stack guard page. So can anybody sort of outline a strategy for defending ourselves against the user process intentionally faulting on crazy addresses?
Isn't there like a max virtual address?
Yes, there is, and that will actually come up. But the top of the user address space is below max VA, and the like the stack guard page, which we shouldn't be allowing, right? Certainly shouldn't be treating as a copy on write thing. All right, I will, I'll show a solution here. We're just gonna call walk for now. And one thing that can go wrong is walk doesn't find a page table entry. So for most illegal pages that a process might refer to, there's no PTE. And there's only a few exceptions to that. So if we detect the illegal, if we detect the PTE not found return value from walk and return -1, we've handled almost every case. The only cases I'm aware of where walk would return a page table entry, but we don't want to allow writes to it, are for the trampoline, trap frame, and stack guard pages. And those all have PTEU clear. So the way I'm going to detect crazy addresses, illegal addresses, is by checking that PTEU is set. And I'll also, just for chuckles, look at PTEV. And if either of those is clear, then we know this is like not an OK address. And we'll just return -1, which will kill the process. So I believe we've taken care of all the illegal addresses the user process could try to use. All right, how can we find out? We want to do a copy now. We want to make this process a copy of the page. How do we find the page to copy from?
I have a question here.
Please.
Wouldn't the strategy of using the PTEU to judge if the page is if it's a legit page for copy and write, wouldn't the strategy not be very good for the long-term process? Maybe you add some other part to the address space, which is supposed to be a writable, which is only supposed to be readable, but that doesn't get taken care of here. As in, you'll have to come back here again.
You're absolutely right. If we were to add any other interesting paging feature, like maybe lazy page allocation, for example, we'd have to revisit these decisions and come up with some other strategy for deciding, is this a copy and write page? Is this a lazy allocation page? Is this a paged out to disk page? Is this a memory map file? And we'd need more sophisticated, in the end, I think most serious operating systems actually keep their own data structure, nothing to do with not a page table, but sort of mimicking a page table that describes the process's address space and sort of describes what each page means and what its state is. And we'd have to consult that table. But for this lab, since we don't have those other features and we're not sure what they would be, I'm just going to do something straightforward. And indeed, we would have to come back and fix it if we made XV6 more sophisticated.
Wouldn't that panic if VA is more than max VA because of the walk?
Gosh, maybe it would. Yeah, well, look at that. Yeah, maybe if the process. Yeah, I think you're right. Well, that's too bad. Okay, so we would certainly. You're right. All right. Well, I was wrong about this.
Wait, can you just return a -1 if you just check the max VA?
I think the observation is that if the user tries to program tries to write a very large address, of course, it can't expect to survive that. But what we would do here is call walk with a very large address. And I'm looking at here the implementation of walk and it's going to panic.
I think we can just use the same approach as walk address does. I had this same bug.
Yeah.
We can just return -1 like other people were saying if VA is greater than max VA before walk.
What I'm upset about is that the tests don't seem to test this, because I didn't put this in my solution. Okay. Okay. Okay, so how do we find out? We want to copy the page. How do I get a pointer to the pointer to something I can copy?
The PTA to PA.
Yeah. So it's just in the PTE. And where am I going to copy to? What should I copy to?
A nearly allocated page.
Yeah. So I just call kalloc. Of course, kalloc is likely to fail, so I got to catch that. We're actually going to see this. So I'm going to put in a print statement so we know. Okay, now we have two.
Should that be PA2? Not PA1.
I actually made this error and I wanted to reproduce it so that we would have to track it down, but you're too clever for me. All right, I want to copy to PA2 from PA1. Okay, so how can I, what do I need to do in order to map this page, this new page, PA2, into the address space? What should I type?
There's like two broad ways. There's either unmapping and then mapping with the built-ins that exist, or you could manipulate the bits.
Yeah, well, I am way too lazy to figure out how to use munmap and mmap, so I'm going to just cook up a new page table entry right here.
I have a question. So
please.
actually, I ran into this issue in almost every lab in which I somehow needed to remap things, and because it occurred so often, I implemented a map that which could remap basically, and I was wondering, is that a bad design choice? Is it like dangerous to
No,
allow remapping?
That's totally reasonable. You know, the functions in XV6 are you know, specialized to XV6 as it exists, and so they, you know, they make assumptions about how the other code works. They have panics in them that are intended to catch other code using them in unexpected ways. But if you change the way XV6 works and you need to do different things, then it's totally reasonable to modify, you know, oh, you need to be able to remap this without a panic. Well, old XV6 never needs to do that. But your code does, so you should feel free to modify anything you need to. Okay, so the deal is here we had a write protected page that was probably shared with another process. What do we have to do to that other process at this point? What do we need to do to the other process?
We can just not do anything, and then when a page faults, we allocate a new page and remove the original one.
That's absolutely right. So you could imagine doing something, but it would be quite complex to do it correctly. And so we just do nothing. And if the other process never writes this page, well, it's not a problem. If it does write a page, then it'll go through all this, it'll make a copy, and it'll proceed safely as well. So doing nothing is totally reasonable. Okay, so now we're going to return. The return value of 0 says there was no error, and hopefully the process will.
But we should free the physical page, right? Or are we not there yet?
Well, we could do it or not.
I guess if we're going in steps, we shouldn't. Yeah.
So if I did this, what would happen?
Well, we would definitely crash right now.
All right, so let's not do this. Or I don't know if we would crash, but we would then be, if we freed a page, it would be presumably PA1, because we better not free PA2 because we're using PA2. If we free PA1, that means the other process has got a problem. it is now mapped into its address space and presumably using, executing instructions in, or I don't know what, a page that we just freed and might be reusing for some other purpose and writing something else over. So I'm reluctant to free it. Although it's, oh yeah, so sadly, among many other things, XV6 walk is never called from outside of vm.c in ordinary XV6, but now we're doing it. All right, where were we? Okay. Remember the very first page fault we got was an scos2. Why are we getting scos2 page faults? It's an illegal instruction. Like, this is the next problem. We have to solve this problem now. What's gone wrong? Or what are some plausible guesses for what might have gone wrong? So the sequence when I type cow test, what we think happens is that the shell forks, it's copy and write fork. We have the child running the shell's instructions, probably taking store faults, but we're handling those store faults correctly. And then the child copy of the shell execs cow test. What bad thing might that do to the parent shell? Well, when you call exec, the implementation of exec frees up all the process's current pages and then allocates new pages to load the file into that you're execing. What's going to happen in the child shell that calls exec when it frees all of its pages? What's that going to do to the parent shell?
Is it
It's going to end up
accidentally? Oh, sorry. Is it going to accidentally free the shell's pages?
Yes, we're going to free every single one of the shell's pages except the one or two that were written. So this includes the shell's instruction pages, and then we're going to reallocate them. They're going to be instantly reallocated by exec to hold other stuff loaded from the file that we're running, cow test. So that's going to totally change everything in the shell underfoot, and unsurprisingly, it's going to instantly crash. So we have to not free those pages somehow. Does everyone see that?
I have a good question. What does the SCPC here point to? Which assembly file would you find that instruction in?
Well,
you said it's shell, right? It's
well, last time was for some other fault somewhere else. It was shell. What it is here, I actually don't know. I never. I did not, unfortunately, take the time to track this down. So one problem with any answer, even if I could give you an answer, so the answer is either the shell or cow test. For process ID 3, that again is it's probably cow test. I have to say I don't completely know what's going on here. Looking at the ASM file is unlikely to be helpful, because the whole problem that we believe has happened is that the page holding the instructions was freed and reused. And so they were therefore not executing the instructions in the ASM file anymore.
Right.
We're executing some garbage.
That makes sense, yeah.
So we could look at the address 1004, but it wouldn't really tell us what had happened. We probably could find this out using the debugger. We could break in GDB and then look at the instructions, it's actually at whatever virtual address 1004 points to.
Quick follow-up question about that fault. So my understanding is that we're getting like an invalid instruction fault because like we're changing the instruction physical memory underfoot, and like the memory is just being written to something else. Is it possible that like in some lucky case that they are being rewritten, but when we look at it again, it's being rewritten to valid instruction pages, so we actually just start executing like random instructions and we don't actually get an invalid instruction fault, we get some other fault?
Yes, absolutely.
Okay.
Absolutely. Yeah. I mean, really, we're now, like, anything could happen.
I see.
I would not have been able to guess. If I had not done this lab, I wouldn't be able to guess what would go wrong at this point. And indeed, I think I have seen other strange things happen at this point. Because maybe the data, maybe the first page that has garbage in it actually has data in it, and the shell trips over some complete garbage data, like a stack, instead of instructions. Okay, so we don't want to free the page right away. We only want to free the page when it's really not being used anymore. So can anybody propose a sort of criterion for when we should or shouldn't free each page of memory?
We could keep track of like how many times, or like basically whenever in kalloc, whenever you should increment and decrement some type of variable and keep an array of like all of the different addresses.
Yes, yeah, exactly. So one way to think about this is that we want to only free a page when there's 0 page tables that refer to it. But there could be many. If a program forks and then forks again and then forks again, boy, we can now have like 3 or 4 different processes that all refer, due to copy and write fork, to this one page. So this count of how many page tables refer to a page can go up due to fork, and it can go back down when a process exits or calls exec. It clears all these references out of its page table entry, or if a process actually does a write and causes a write fault, that's also a situation in which we have one fewer reference from one fewer page tables referring to a page. So we want to keep a count, and we want to be counting the number of page table entries that refer to a page. So we're going to need to think about how to maintain this count and when to increment it, like exactly where in the code to increment it and decrement it. Okay, so there's, as you may be aware, there's multiple ways to maintain this count. The way I do it is I make an array called ref count. It's just going to have for every page a count. We need to know how many entries are in ref count. In XV6, it's so simple that it just uses a fixed amount of memory, physical memory, right? We only need to keep a count per page of physical memory. We know that from inspecting KNet that XV6 uses only phystop amount of physical memory. We only need to keep a count per page, not per byte. So we're going to divide phystop by 4096. And that's how many array elements we need. In a more serious operating system where we don't know how much memory is available until we inspect the hardware, we would have to allocate this array dynamically. Any questions about where to put the counts? All right.
Actually, yes. I'm wondering, is there a reason that you're using 4096 specifically and not the page size macro?
Yeah, the reason is that I can remember 4096 and I don't remember the name of the page size macro, but I'm happy to use it if you like. I mean, if XV6 was intended to be portable and to be able to run on all kinds of different machines with different page sizes, we'd have to be much more careful about this. But there's 500 ways in which XV6 is totally not portable. So I don't worry about it.
Is page size is determined in hardware, and I guess where?
In the hardware. The RISC-V manual says how big a page is. Yeah, because the it's the MMU that takes a virtual address and uses it to index into the page table.
Oh, right, because the address translation happens in hardware, so the hardware has to know how big the pages are. Okay, that makes sense.
It's configurable, but there's a couple of different strategies you can tell the hardware to use, but we tell it to use 4096 byte pages. Okay.
Sorry, quick question. So where are, I guess this is a C question. So where are like global variables like ref count stored? Or like what? Like, are they associated with a specific process or?
This is the kernel. What's going on is that the file, the executable file that the compiler and the loader or linker produces has a indicates how much data, how the total size of all the global variables in the program. And so we don't see the code for this, but when QEMU loads the kernel, well, what's really going on is that when you compile, the program called the linker figures out based on, looks at all the global variables and their sizes and assigns an address in memory, to each global variable. And that's where it lives in memory. I mean, and we just arranged that, so the XV6 kernel uses, I don't know, 10,000 bytes of various global variables. And wherever the boot process loads it into memory, say at address 1,000,000, it just uses those addresses for the global variables.
I see. Is this similar to how like there's only one copy of like the instructions for a program on disk, and there's only like one copy of the kind of global variables for that program on disk?
Well, a program like this, well, I'm not really sure how to answer this. I mean, when you declare a global variable like index, when you compile, the compiler and the linker just decide based on who knows what, or it's configurable, but they decide the address for that variable. They decide, all right, boy, X is going to go to address 1,000. And then the code that reads or write X, if we have code that says, ref count of 0 equals 1, what that compiled into was just setting the memory at address 1,000 or wherever the linker decided to put ref count. We just does a store to set the memory at address 1,000 to 1. Yeah. It's actually almost exactly the same thing that happens when you run an ordinary user program. The linker and the compiler decide where in memory global variables are, and they just read and write there, and it just works. I'm sorry if that's not much of an explanation. All right, so we just define this global array of counts, 1 per physical page. And we need to modify these counts in various places. Certainly when we first allocate a page, we're going to say that it has 1 reference because we return an address to the page to whoever called kalloc. And at the moment, only that program has a reference to this page. So I'm just going to set the ref count for this page to be 1. So first of all, I'm just going to calculate the page number, which is the address of the page divided by 4096. That's the page number. And then I'm going to set the reference count for the page we just allocated to 1. Any questions about this code? Just because I know that I'm going to have bugs with reference counting, I'm actually going to do a little bit of a sanity check here and just that, the reference count really should be 0 if the pages, we just allocated a page that was free. Boy, it better have a reference count of 0. All right. Any questions about this code? All right, so in general, we want to increment the reference count when when copy and write fork adds a page table entry that points to an existing page. And we want to decrement the reference count, as it turns out, in many places. For example, when a process exits, we need to decrement the reference count of all its pages. When you call exec, and that frees all the current memory because it's going to replace it, we want to decrement all those reference counts. When a copy and write page fault happens and we make a copy, we want to decrement a reference count on the old page. It turns out these are all the same places that currently free a page, because the current XV6 thinks there's only ever one reference to each page. So in most of the places we care about where we want to decrement, there's currently called a k-free. So what I'm going to do is modify k-free to have somewhat different semantics, and to have k-free be sort of a function that decrements the reference count and frees the page only if the reference count has dropped to 0. And that will just automatically fix all the places that call k-free. All right, so we need to actually do the check before we fill the page with junk. So this makes the k-free a little bit more complicated, because even though there's a critical section with locks and k-free already, we can't use it because it happens after the point at which we filled the page with garbage. We need to lock, because we could be freeing the same page at the same time from multiple different cores. Again, I'm going to find the page number by dividing the physical address by 4096. I want to panic. Again, just a sanity check. Gosh, if we're freeing a page, it better have more than 0 ref counts. We need to return if the page has more than one reference count to it. Or actually, let's decrement the reference count. We want to return after we release locks, and so we have to remember a variable. We're going to sort of remember whether the page has more references, and then release locks, and then return. So I'm going to make a temporary variable which has the and release. Then say if there's still references to this page, let's just return and not free it. And only if the reference count dropped to 0 do we free it. Any questions?
Can you explain again why you have to acquire the kmem lock during the process?
Why I have to acquire it at all?
Yeah, when you're doing the page number calculations. And
it's this line. Really, is this line and the next line that are the problem. The issue is that on this page, we now likely has more than one reference to it. And so if two processes with a reference to the same, with a page table entry pointing to the same page, if they both exit at the same time on different cores, they're both going to call k-free for the same page at the same time.
Oh, I see.
Yeah.
Could you just create a new lock for the reference count variable and use that as well?
Yes.
Cool.
Yes. Yeah, basically everybody, all code that manipulates these counts needs to use the same lock, but I don't think it matters what lock it is. Okay, so this takes care of most of the decrements we care about. Every time a page is free, we're really going to only free it if the reference count has fallen to 0. We also need to increment the reference count. Where do we need to increment the reference count? Well, because I know we're going to need to do it. I'm going to write the function that anybody can call. Again, I want to panic if something is weird. So if the address is wacky, I certainly don't want to go beyond the end of the array. Or if we don't want to increment the reference count of a page whose reference count is currently 0, that's also an error. And I'm just putting these in there because I know from experience with my code that this is exactly the kind of place I'm going to have a bug in. All right, where should I call incref from?
UVM copy when you.
Yeah, I think UVM's copy is the only place that makes another reference to a page. All right, gosh, where am I going to put this? Well, it almost doesn't really matter. All right, we're making another reference to PA. So we want to say incref PA. And we're likely to run into trouble from the compiler if we don't put a definition for it in traps.h, whatever. Okay. All right, let's see. Well, that was pretty quick. All right, what's kfreeref? Oh, kfree is unhappy. Okay, well, here's the time. We don't know. This is very early in the boot process, which is maybe a hint as to what's going wrong. If anybody has any guesses, I'd be happy to hear them. Meanwhile, I'll just fire up the debugger to try to get a backtrace.
It is during KNet because you're trying to put things into the linked list and you haven't allocated yet. So you when you trying to load everything into the linked list, you haven't called kalog before that.
Yeah, that's exactly right. So we'll just see that in action here. Okay, I got the panic, I type where, and it's in, here's kfree being called in panicked, and it's being called from free range right at the beginning when we're initializing the free list, indeed. So there's something to be fixed in free range. The problem is I'm calling kfree as you said, I'm calling kfree, but of course all the reference counts are 0 and kfree panics if the reference count is 0. So I'll just hack this to be how about that? Okay, we managed to boot now. Boy, I wonder if we're done. Let's see. Okay, so let's run the cow tests again. At least we passed the simple test. Aha! So we passed the simple test, which is great, and we passed one time through the 3 test, but we didn't make it through the second time through the 3 test. And the 3 tests triggered the print statement that I added to trap, which said cow kalog failed, which only would print it if we're out of memory. So we're out of memory. Why are we out of memory?
So we've updated reference counts every time we've allocated, but we haven't decremented counts whenever we've tried to free, right?
So where should I add a...
But with your current approach, I think PA1, that reference count needs to get decremented. So we would need to k-free it.
Yeah, exactly. So I think somebody actually, possibly you brought this up 45 minutes ago. Let's see. Let's free PA1, not PA2. Okay, and so now what k-free means now is not free this page. It's what k-free means is decrement the ref count on this page and free it if it's 0. And so if we're in a simple situation where there was just one fork, and so there were 2 references to the page, and we've taken a write fault and made a copy, where now all k-free is going to do is decrement the count to be 1, and now the other process can use the page. We're not actually going to free it. Okay, so hopefully now we'll not run out of memory in CowTest. I love it. Okay, we made it through the 3 test without running out of memory. All right. But we're not done, sadly. We have this interesting error in the file test. So let's take a look at the file test. All right, so here's the file test. And it says right in the comment for the test that it's investigating copy out. So a good hint of where our problem is going to be. The thing that actually failed is, I mean, you have to use your imagination a little bit, but the error message seems to be this one, printed from 2 different processes at the same time. And indeed, this is a loop. This test is a loop that for 4 iterations just forks. And so it's going to produce 4 concurrent processes whose error messages will be interleaved. So we need to know why that read failed. If we want to understand what the bug is, we need to know why the read failed. So the first step is maybe to figure out what the read actually returned. All we know is that it returned something other than size of I, but we want to know what it returned. So I'm going to capture the return value. And I'm going to print the return value. So at least know what it is we're facing.
Oh, I have a question, sorry. It seems like 3 of the threads failed, but 1 of them didn't, and it seems like it's still running. Why is it not failing?
Why did the 3rd thread not fail?
The 4th.
Why did the 4th?
So like if you do CowTest and then echo, that other one is still going to be running and you're going to see more output.
Yeah, 3 failed and 1 didn't. Let's just finish investigating why any of them failed, and then I can make a guess, although I don't really know why one of them didn't fail. Okay, so what's happening here is that read is returning -1. So why is read returning -1? You might hypothesize that read, we're passing this buffer into read. You might imagine that the read needs to do something, namely call copy out, to copy file data into this buffer that we pass to read. And maybe something's going wrong with that in its relationship to copy and write fork. So let's take a look at read and see why it's failing. Try to track down why read is. All right, so let's capture what read, all sysread does is the system calls file read after fetching a bunch of arguments. So we'll fix this to take us one step closer to understanding why things are going wrong. Right? We're expecting CC to be -1. Ah, that's interesting. We never saw CC equals -1. In fact, the failure occurred. The failure starts occurring here before we get any corresponding CC print statements, and it's not -1 at all. It's 4, which is a non-failure value. So what that means is that something before the call to file read must have triggered this return. So one of these functions here has caused read to return -1. Please feel free to guess while I'm typing. This was a complete surprise to me, by the way, when I tracked it down.
I think it's the file descriptor.
Yeah, the file descriptor. What I expected was that file read was failing due to something in copy out not doing the right thing with copy on write pages. But that is not at all where the failure is. Okay, so if we want to find out, like, it's either argfd or argint or argatter that's failing, let's start with argfd. I'm just going to stick print statements in here to help me figure out which one of these failure cases is actually triggering. There's only 2 places it returns -1. And this one, there's something wrong with the FD itself. Right, so we're going to get these print statements on cases where argfd returns -1. What does this mean? FD. All right, so that we expect these FD printouts to occur just before the error. So what we saw is FD9. It was FD9 this causes the error. So FD9 failed one of these 3 tests. Well, we know it's not less than 0. I happen to know it's not greater than or equal to NO file for number of open files. And so that means that the O file array for 9, file descriptor 9, must have been 0. That is, in this process, there is no file descriptor 9. So somehow, copy on write test, this code in the copy on write test is passing an invalid file descriptor to read. So this file descriptor comes from FDS. FDS comes from a call to pipe. How could usually pipe, if it doesn't fail, it leaves the file descriptor in the array. So how could this go wrong? Well, we all know the answer has to be blah, 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 copy out. So what's the missing piece?
I mean, I guess like one thing that helped me track this down is I realized, at least first of all, FD should not be 9 on every iteration. 9 is kind of the value that you would expect kind of on the last iteration. That's kind of like the highest call to pipe.
Yeah, they all got 9. You're right.
So something, they're kind of touching each other's memory, which is strange.
Yeah, that's exactly right. So, you know, the FDS pipe, the way pipe returns the file descriptors is that it calls copy out to copy the file descriptor number that is allocated into the caller's address space. Well, we're using copy on write fork here. So if we're not careful, so at least initially, there's just one page and it's shared among all the processes. So the first process that calls pipe, if something goes wrong, the pipe system call might conceivably write the shared page, and that value, that file descriptor, will then be seen by all the processes instead of just the process that actually allocated the descriptor. So everybody see this as a kind of at least hypothetical risk. So let's look at try to imagine. Well, so first, let's look at sysfile to see how pipe copies out the file descriptors it allocates. And indeed, down here are these two calls to copy out, to copy the two elements of that pipe array. So pipe is using copy out to copy the file descriptor numbers into the array in user space. So what does copy out do? Well, it looks up the virtual address to find a physical address. And then it writes, it copies over that physical address, and that's it. So one thing it is not doing is checking for write permission. It doesn't look at PTEW. And so if this page, if this virtual address refers to a copy on write shared page, copy out just has no idea, it just goes ahead and writes it. And so I mean, indeed, when pipe calls copy out, it's going to be writing a shared page so that all of the forked processes see this modification, not just the process that called pipe. Any questions about why this is happening? Okay. All right, so as you all know, we need to modify copy out to, since copy out is, looking up a virtual address and translating to a physical address, but it is not using the MMU. So the MMU doesn't catch the write fault because the MMU is not involved. WalkAdder looks at the page table itself instead of basically getting the MMU to look at the page table for it. Okay, so we need to modify copy out. We don't want to call WalkAdder. WalkAdder just produces a physical address. We actually want the page table entry because we want to look at the permission bits to see if it's a copy on write, a write protected page. So we're going to call walk instead. We need to check all the usual errors. So maybe there's no mapping at all. Maybe it's not a valid mapping, or maybe it's a mapping that the user code is not allowed to use. And in all those cases, it's an error. But this time we can actually return an error, which we'll call just read to return -1 instead of killing the process. So that's nice. Next, we need to know how to check whether it's a copy on write page. Any ideas for how we can check whether we should apply copy, whether we should do a copy at this point? What's different between copy and write pages and just sort of ordinary unshared pages?
Would the reference count be large?
That's a good point. If the reference count was greater than 1, that'd certainly be a very strong hint that's a copy on write page. But if the reference count is 1, does that mean it's not a copy on write page? It turns out if you fork and the child takes a copy on write fault and makes a copy, that reduces the reference count to 1, but the page is still write protected in the parent. And actually probably we could get away with modifying in that case. So I think we actually could check the reference count and only treat it as a copy on write page if the reference count is greater than 0. But what I'm going to do is a different, an even easier shortcut and say, if the page is write protected, the only way a page can be write protected and have the PTEU bit set in this version of XV6 is if it's a copy on write page. So this saves me a little bit of typing compared to checking the reference count. We already wrote the code to deal with this in trap.c. So I'm just going to call that code from here. We still have to deal with the possible error return if it's a crazy address. Oh, actually, we don't. All right, so if the page is not writable, we're just going to call copy and write fault. And copy and write fault, does the copy and it makes the page writable. So I think we're almost done at this point. However, if COW fault did make a we gotta get rid of this. If COW fault did make a copy, it's going to have modified the physical address in the page table entry. So we have to pull that physical address out of the page table entry again in case it was changed. I'm just going to do that since we have the page table entry right here. And I think this is more or less enough. So any questions about the modification to copy out? All right, I got to make a global declaration for COW fault. Beautiful. All right, that's looking great. Anybody happen to know if we're done? We may or may not be. We also have to pass user tests. Oh, all right, let me get rid of this. These print statements. I think the exec out test intentionally allocates a lot of memory. All right, any questions while we wait for the verdict from user tests? Oop. Aha. Okay, user test was unhappy. I think this is a familiar piece of damage, which somebody has brought up already. It's the panic and walk. If the user process, the user test actually, I think, does intentionally, we'll take a look at user tests. And it's the copy out test. And it even says in the comment, it passes ridiculous pointers to system calls. All right, so what we're faced with is copy out. We pass in a ridiculous pointer. It's simply called walk with that ridiculous pointer. And walk panics if you give it a ridiculous pointer. So as somebody mentioned, we need to not call walk with ridiculous pointers. What is it, max VA or something? All right. And of course, we're totally entitled to return an error if a user process passes us a out of bounds pointer. All right, I'm just hoping it passes now. I'm not aware of any other problems. Okay. Questions?
I guess my question is more broad. Like we saw when we were doing that with small steps, we were getting random bugs at every step. And if we're doing the lab from scratch, then wouldn't it be confusing to get all of those weird bugs? And how would you know whether it's a bug with something you wrote or a bug because you didn't write the rest of it?
I'm afraid I cannot answer your question. The sad truth about bugs, particularly bugs caused by doing funny things to page tables inside the kernel, is that every bug is different. And how what turns out to be the winning strategy for tracking a bug down, it just depends totally on the nature of the bug. my usual, and I have a sort of a collection of strategies that are sometimes helpful and sometimes not. Like I'm a huge believer in putting print statements into the code in order to gather information or to verify hypotheses. I'll often spend time just looking at the code just for the purpose of generating, sort of brainstorming with myself to just try to generate, things that could possibly be going wrong at this point, and then put print statements in or panics or something to try to rule in or rule out various guesses at what the problem might be. Another possibility is that you've made some, your code worked or didn't show this error or something, half an hour ago, and then you made some changes and now you have some bug. So another possibility is to, if you can, back up to a version of the code that didn't have the bug and sort of add your changes bit by bit until the bug shows up. I mean, none of these are, I don't know any strategy that always works or even works more than a fraction of the time. But the truth is, part of what you're learning in this class, as well as learning about operating systems, you're getting experience writing and debugging code. Sorry not to be more helpful. Other questions? All right. We're at that end of class time. I'm happy to talk more, but we're done with the formal part of this class. All right, and to see you all on Wednesday.
Oh, sorry, I actually have another question. When we were seeing our first write fault, we also saw after that for the shell a legal instruction fault, and then something for the init process. What was that?
Well, I don't have a theory. The init process, I don't think would share pages with anything. I just don't know. I'm sorry. We could, I would have to back up. But this happened very early when I was doing the lab, right? We just had a copy of the page table, nothing else.
Yeah,
So,
I think it was a like scos F for the shell, and I think scos C for the init process, maybe.
All right, let's see. If you really, let's see. We can. Let's reconstruct the lab from scratch. So I'm gonna clone. Okay, at this point we had just made changes to UVM copy, right? So we were, what are we not doing here? We're not allocating, and we're not doing mmove. But we are, we're going to pass PA to map pages, and well, I think was the very first time I ran anything. I think this was the state of play.
It was after we did the flags also.
Okay. All right, so let's clear. And does that look good? We got a C. Well, what's C? C is instruction page fault. Oh, this so okay. So scal's 2. Is we think a shared in process ID 2. Oh man, you're right. It's process ID 1. I just don't have a theory for why process ID 1 might have run its trouble. Let's look at what init does. Is this init? What is it? Gosh, what is it called? Okay, it execs the shell. I don't know. Okay. Oh, here's an idea. Process ID 2 is taking a fault and is exited.
So you do a fork later, like right.
Yeah. And so that means that this wait in init has returned.
Yeah.
Right. And so it's going to go back around the loop and call fork again. And so, after a fork, we're now sharing and, depending on all this damage code.
Oh, okay, I see.
Yeah.
Okay, yeah, that's very confusing.
Oh yeah, these errors are just like complete bananas because we violated all sorts of intuitions about how things should work. Okay. Anything